Hey guys, in this video we're going to go over everything that you need for your first physics paper for OCR Gateway. Now to go with this, there is the free revision guide which you can download from my website. Go along with this, the video, you can tick off what you do know, what you don't know, which areas you need to focus on for your revision. And then to help you as well, there are the predicted papers, the practice workbooks and the thousands of multiple choice questions just waiting for you. An atom is incredibly tiny. The word atom means uncuttable, and it's so tiny that the Greeks who named it an atom thought it was the smallest thing, but it isn't the smallest thing. We know there are things inside of it. Now, I said it was incredibly tiny. Its size is 0.1 to 0.5 nanometers, which is 1 times 10 to the minus 10 to 5 times 10 to the minus 10 meters. Now, inside our atom, we have protons and neutrons, and in the shells on the outside, we have electrons. This bit in the middle here, this is called a nucleus. Protons and neutrons are located in the nucleus, whereas electrons are in the outer shells. Protons have a mass of 1, neutrons have a mass of 1, and electrons are incredibly tiny. Their mass is 1/2000th that of mass of a proton or a neutron. Protons have a charge of +1, neutrons have no overall charge, and electrons have a charge of -1. Here we have boron. The mass number is 11. The atomic number is 5. So if you want to find the number of neutrons, that is mass minus atomic. 11 minus 5 gives us 6. Protons equal 5. Electrons equal 5. Now, protons have a positive charge, 1, 2, 3, 4, 5. Electrons have a negative charge, 1, 2, 3, 4, 5. So an atom, and this is for an atom only, will have the same number of positive charges and negative charges, which means there is going to be no overall charge in an atom. An ion is going to have lost or gained electrons. So for example, if we have take our boron again, with our 1, 2, 3, 4, 5 positive and 1, 2, 3, 4, 5 negative charges, if it loses an electron, it now no longer has the same number of positive and negative charges, so it's going to be charged. It has created an ion. On the periodic table, you will see two numbers. The larger number of the two is the mass number. The smaller number of the two is the atomic number. It does not matter where these are located. Different books, exam boards are going to put these in different locations. It does not matter where these are located. The mass number is equal to the number of protons plus the number of neutrons. The atomic number is equal to the number of protons and also equal to the number of electrons in an atom. So if you want to find the number of protons, that is equal to the atomic number. Whereas if you want to find the number of neutrons, that is equal to the mass number minus the atomic number. The model of the atom has changed a lot over time, and it's changed because we have new developments and new discoveries. From ancient Greece, where they developed the word atom, uncuttable, to Dalton, where it was a solid sphere, J.J. Thomson, who discovered the electrons, where we had a plum pudding model, a positive sphere with negative bits dotted through it, Rutherford, who did the plum pudding experiment and worked out that it had a solid centre, Bohr, who developed the nuclear model of the atom. Now I know the writing is very small on here, that's because you don't need to know the exact details, you just need to know the overall developments. Rutherford gave us the positive centre, which we call the nucleus. Chadwick added in neutrons, and then Bohr developed this nuclear model that we use today, with a positive centre and electrons orbiting outside. Solid particles are in a fixed position. They do vibrate, but very, very slightly, and it is around a fixed position. They do not move around. Liquid particles move around much more. They're still touching each other, but they are not in a fixed position. They are moving about randomly. It's still rather limited movement. It's still within a confined space. Unlike gas, which is free to move and zip around all over the place. If we're going to be putting energy in, then we are going to be turning a solid into a liquid, or we are going to be evaporating a liquid into a gas. If energy is coming out of the system, a gas is going to be condensing or a liquid is going to be freezing. Density is the amount of mass in a set volume. So, mass in a set volume. And this is the same for the equation. And the equation for this is rho. I know it looks like a lowercase p, but it's not. It's a lowercase rho. Equals mass over volume. The units you need to know for this: mass is measured in kilograms, volume is measured in meters cubed, and density is measured in kilograms per meters cubed. Specific heat capacity is how much energy is needed to raise the temperature of 1 kilogram of a substance by 1 degree. Our equation for that is change in energy equals mass times specific heat capacity times change in temperature. Specific heat capacity is going to be particular to whatever substance they're talking about, and they would tell you this. I wouldn't expect them to expect you to know this. Our units for energy are joules, our units for mass, kilograms, our units of change in temperature are degrees C, and specific heat capacity is joules per kilogram degrees C. There is not an extra per in here, that is a space in there. Specific latent heat is how much energy is needed to change a substance from a solid to a liquid at the melting point. And remember, if a substance is pure, it will change instantly at one temperature. The equation for this is energy equals mass times specific latent heat. Our units for this are going to be joules for energy, mass is going to be measured in kilograms, and specific latent heat is joules per kilogram. When we're looking at the collection of molecules in a system and the amount of energy they have, we are going to have two bell-shaped curves. At low temperatures, there are going to be more molecules that have less energy and few molecules that have high energy. Now, if we say that this point here is where molecules have enough energy to evaporate, then only these ones at low temperature can evaporate.
However, at high temperature, more molecules have more energy. So there's still going to be some with a low temperature, but the majority of them are now going to have a high temperature, meaning more of them are going to have passed this threshold for evaporation. And the average kinetic energy is going to be the area under the graph. So as molecules evaporate, they're going to be leaving this section of the graph. So evaporation is actually going to lower the average kinetic energy of a system. In this video, I'm using a simulation from the excellent PhET website. You can see here we have a closed container and I'm adding in gas here and we can see the pressure. As the more gas goes in, we can see the pressure is increasing. So it's stabilised. I'm going to add in lots more gas here, and you can see the pressure is going to increase. So as the gas bumps against the walls of the container, it's exerting a small force, it's doing work on there, and is going to be increasing the pressure in the system. Pressure equals force over area. The units for pressure are pascals. For force it is newtons, and for area it is meters squared. I have seen exam questions which use newtons per meter squared for pressure. If they do that in the exam question, give your answer in the same format. I've also seen exam questions where they've done newtons per centimetre squared. So if the question is in that format, give your answer in that format. This is one that you have to pay attention to because they could be sneaky here. If we want to work out the pressure in the system, that is volume times the constant. The constant you'll be told in the exam. Our units for pressure are pascals. Our units for volume are meters cubed. A scalar quantity is going to be just a number. A vector quantity is going to be a number and a direction. For example, distance is scalar, but displacement is vector because it's distance in a direction. Mass is scalar, but weight, which is your mass upon the earth, is vector. Speed is scalar, but velocity, which is speed in a certain direction, is vector. Acceleration and force are both vector, and momentum is also vector. Distance equals speed times time. Distance is measured in meters. Speed or velocity is measured in meters per second. Time is measured in seconds. Distance time graphs tell us lots of information. If we have a slope that is increasing, we are moving. And the steeper the slope, the faster we're moving. If it is a flat line, it is not moving. We can see that as time is increasing, our distance is not increasing. So in a distance time graph, the flat bit is not moving. We can calculate speed as the gradient. Gradient is up over across, which is going to be distance over time. Velocity time graphs look very, very similar to distance time graphs, but are different. For example, at our flat bit here, it is now moving, but it is going at a steady speed. We can see that when they are increasing, they are accelerating. So we now know that acceleration is equal to the gradient. That's up over across, or velocity over time. If we want to work out the distance travelled, that's the area under the graph. For this section here, it is a triangle, so to work that out it's going to be half times base times height. For this section here, that is a rectangle, so that is going to be base times height. This section in the middle here is a bit more complicated because we have a triangle, a rectangle, and a triangle. So that is base times height plus half times base times height. And the height is the height of the triangle there. To work out acceleration from velocities, we have acceleration equals final velocity minus initial velocity over time taken. Velocity is measured in meters per second, whether that is final or initial velocity. Acceleration is measured in meters per second squared, and time taken is measured in seconds. Final velocity squared minus initial velocity squared is equal to 2 times acceleration times distance. Velocity, final and initial, is measured in meters per second. Acceleration is in meters per second squared, and distance is in meters. We can say that force is equal to mass times final velocity minus mass times initial velocity over time taken. Where force is measured in newtons, mass is measured in kilograms, final velocity in meters per second, mass again in kilograms, initial velocity in meters per second, and time taken in seconds. If we're looking for the resultant force, we need to find the difference between them. For example, here we have 10 plus 10 newtons minus 5 newtons is going to give us plus 5 newtons, which is going to be 5 newtons in that direction. For the second one, we have plus 2 newtons minus plus 2 newtons, giving us 0 newtons as overall resultant force, so there is going to be no movement. When you are falling, when something is falling, terminal velocity is going to be reached when all forces are balanced. A velocity time graph for this would be very fast acceleration as the object initially started to fall. As the object started to balance out, that would slow, and when they reach terminal velocity, there would be no further increase in speed. When you're free falling under gravity, your speed is going to be 9.8 meters per second, which is the same as the value of gravity, which is 9.8 newtons per kilogram. Force equals mass times acceleration. Force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. Centripetal force is just the resultant force when things are moving in a circle. So if we have our centre of a circle here and our object here, it is moving in this direction, except it's being forced round into a circle here, here. But at each point, what it wants to do is to move in a straight line. However, it's being forced around in a circle. And because it's being forced around a circle, we can see it has a constant speed but changing velocity, because velocity is speed in a certain direction. Momentum is mass times velocity. Mass is measured in kilograms, velocity is measured in meters per second, and the momentum is measured in kilogram with a space meters per second. I know there's a temptation to put another line in there, but that would be wrong. The law of conservation of momentum says that momentum is always conserved, which in calculations means your momentum before is going to equal your momentum afterwards. So if you have two objects colliding, their momentum together before is equal to the colliding combined object afterwards. Here we have a Newton's cradle, which really elegantly demonstrates a number of physics principles. First of all, inertia. An object that is in motion will remain in motion unless acted on by an outside force. An object at rest will remain in rest unless acted on by an outside force. So those balls in the middle are only going to move if something hits them, and those balls on the outside are only going to stop if something stops them. It demonstrates the conservation of energy, where the balls only slow down as they lose energy to other things. In this case you can't hear it, but it's losing energy to sound, and it's losing energy to a bit of friction within the air. This will keep going for as long as there is energy within the system. And it also demonstrates Newton's third law, where for every action there is an equal and opposite reaction. And we can see this as the balls keep hitting each other. Inertia is where an object at rest will remain at rest unless acted upon by a force, and an object in motion will remain in motion unless acted on by an outside force. You can put this into action if you are driving along and you have your seatbelt on, the car brakes. You would not brake as well unless you were acted on by a force, that force being your seatbelt. Conservation of energy. Energy is never created or destroyed, it is only turned into something else. Here it has been turned into sound and a little bit of heat, and for every action there is an equal and opposite reaction. Don't want to overload you with too much maths, but there is a bit more coming, so just take a tiny little break. To calculate work done, that is force times distance. Work done is measured in joules, force is measured in newtons, and distance is measured in meters. And from this we can say that 1 joule is equal to 1 newton meter. To work out kinetic energy, that is half times mass times velocity squared. With kinetic energy being measured in joules, half is just a number, so we don't need units for that. Mass is measured in kilograms, and velocity is measured in meters per second. And it's important to note for this one that here it is just the velocity squared, not the whole thing. Power equals energy transferred over time. The units for power are watts with a capital W, energy transferred is joules with a capital J, and time is seconds with a small s. Power is equal to work done over time. Power is measured in watts, work done is measured in joules, time is measured in seconds. When you exert a force on an object, it is going to be squashed or stretched or deformed in some way. Here I've done an experiment for you. This is commonly known as Hooke's law. What I've done is taken a spring, this is the bottom of the spring, kept marked in every single photo, and I've added weights onto the bottom of it. You can see that the length of the spring is getting longer the more weights are added onto the bottom of it. We can plot what happens in Hooke's law because it is our direct line until we get to a certain point, and this point is the limit of proportionality. Before that, it is going to stretch. So the more force we add on as we increase force, the extension is going to be increased. After we get to the limit of proportionality, no matter how much force you add on, it is not going to stretch anymore. It is potentially going to snap. Force equals the spring constant times extension. Force is measured in newtons, extension is measured in meters, and the spring constant is measured in newtons per meter. If we want to work out the change in gravitational potential energy, that is equal to mass times gravity times the change in height. Gravitational potential energy is measured in joules, mass is measured in kilograms, gravity is 10 newtons per kilogram, and height is measured in meters. Your weight is not the same as your mass because your weight is equal to your mass times gravity. Your weight is measured in newtons, your mass is measured in kilograms, and gravity is measured in newtons per kilogram. So your mass will never change, but your weight will change depending on the planet or depending on gravity, which is why when they went to the moon, they were basically weightless so they could jump around. The value of gravity depends on where you are. The value of gravity on Earth is 10 newtons per kilogram, where on the moon the value for gravity is much less, which is why it looks like they're bouncing around on the moon. However, if you are falling on Earth, we can say that your acceleration due to gravity is 10 meters per second squared. Same number, different units. Charge equals current times time. Charge is measured in coulombs. Current is measured in amps. Time is measured in seconds. You need to know all of these circuit symbols. I've made you handy flashcards for this, but here is a quick recap. This is a cell. This is a battery. You will notice that a battery is more than one cell put together. Here we have an ammeter, voltmeter, a lamp or a bulb, diode, an LED, light emitting diode, resistor, variable resistor, fuse, thermistor, LDR, light dependent resistor, close switch, open switch. Here we have a circuit in series where you can run your finger the whole way through from the battery to all the components. And here we have a series in parallel where it has like branches or ladders. You can't run your finger around everything without going over something twice. You'll notice here we have an ammeter that is in series and our voltmeter that has to be in parallel around the component. Charge is the value of electricity flowing through a circuit. Current is the flow of electrons. Potential difference is what pushes the current around. And resistance is anything that slows down the current. Potential difference equals current times resistance. Potential difference is measured in volts. Current is measured in amps. Resistance is measured in ohms. There are 3 current potential difference graphs you're expected to recognise and draw. Remember, current here is measured in amps and potential difference is measured in volts. A resistor at a constant temperature, the current and potential difference are directly proportional to each other. For a filament bulb, we have our graph going through 0 looking like this. This is because as the temperature increases, the resistance increases. And a diode will only let current flow in one direction, so the graph looks like this, the direction that it is pointing. A thermistor is used in stuff like your central heating, and it's only going to let current flow at certain temperatures. For example, at a high temperature, our graph looks like this. Whereas at our low temperature, the graph is going to look much lower. So as the temperature changes, the resistance changes. For a light-dependent resistor, whether the lights are on or off is going to depend on the quantity of light. We can use this in street lights or security lighting. If we have a bright light, that's what our graph is going to look like. But then if the light dims, it is going to change. So that resistance flowing through the circuit changes with the amount of light. We can think of current as electrons moving around a circuit. And in a series circuit, they all move in the same way. They all move through the same path. So wherever we look in a series circuit, the current is going to be the same. However, in a parallel circuit, the current that comes out of the battery, all of this is going to pass the first ammeter, move down here, and then when it gets to this point, it has two choices of where to go. It can go this way past this ammeter, or down here and this way past this ammeter. So the current gets split. Potential difference measured by a voltmeter. I'm going to measure the voltmeter around the battery, then a voltmeter around each of the bulbs. And you'll notice that the potential difference, the voltage at the battery, is split across the components. Whereas in a parallel circuit, the potential difference that we have here across the battery is the same as we have across each of the branches. Our circuits are getting quite complicated now, and we're going to be looking at resistance. When we have resistors that are in series, the total resistance is just them added together. Whereas when we have resistors that are in parallel, the total resistance is 1 over resistance of resistor number 1 plus 1 over the resistance of resistor number 2, and so on. So, current in a series circuit is going to be the same wherever you look at it, but you have to add up the different potential differences to get the total potential difference, and add up the different resistances to get the total resistance. On a parallel circuit, the current on each branch is going to be equal to the total current, but the potential difference on each branch is going to be the same. To find the total resistance, you need to do 1 over the resistance on each branch. Energy is equal to charge times potential difference. Energy is measured in joules, charge is measured in coulombs, and potential difference is measured in volts. Energy is equal to power times time. Energy is measured in joules, that is capital J. Power is measured in watts with a capital W, and time, seconds with a lowercase s. Power is equal to potential difference times current. Power is measured in watts, that is a capital W. Potential difference is measured in V, and current is measured in amps. Power is equal to the current squared times the resistance. Power is measured in watts, capital W. Current is measured in amps, and resistance is measured in ohms. When we have two like poles, they're going to repel. But when we have two unlike poles, they're going to attract. A permanent magnet is going to have a magnetic field which goes from north to south, and we can induce a magnet, a temporary magnet, if we place something inside that magnetic field. Magnetic materials are going to be metals, and that is going to include iron, nickel, and cobalt. You can easily make an electromagnet at home. All you need is a battery, some wire and an iron nail, because all an electromagnet is an iron core with a wire around it connected up to a current. You can use this to pick up things like paper clips or iron filings. When a current is passed through the wire, it creates a magnetic field around the wire, and this in turn strongly magnetizes the iron bar, thus creating our electromagnet. If you want to change the strength of an electromagnet, you can do two things. You can change the current, or you can change the number of turns or the number of coils that the wire is wrapped around the iron core. The generator effect is just an extension of Fleming's left-hand rule. When we have a wire and we move it through a magnetic field, we are going to be generating a current. For Fleming's left-hand rule, we need to make our left hand in this shape here. So finger pointing out, thumb up, finger out. And your first finger is your magnetic field. This finger here is the current, and then your thumb is the movement of the force. And what you need to do when you have an exam question is literally contort your hand until it fits in the right direction. So first was nice and easy. My field is going in that direction. My current is going in that direction. So the movement of the force is going upwards. This one here is a bit more complicated because this finger needs to be pointing in that direction. My current needs to be going down, and then my thumb is going into the page. We can change the size of the force by changing the current, by changing the strength of the magnet, or by changing the angle between the wire and the magnetic field lines. The greatest force is when the wire is perpendicular with magnetic field lines, and the force is going to be 0 if the wire and the field lines are parallel. Magnetic flux density is the amount of magnetic flux in a certain area, and the equation that we use for this is force equals magnetic flux density times current times length. You'll notice really annoyingly that this is an uppercase I and a lowercase l. Our units for this, for force, are newtons. For magnetic flux density, they are Tesla. For current, it is amps, and for length, that is meters. While this is called a simple electric motor, there's actually quite a lot of physics going on here, and for this we really need to use our Fleming's left-hand rule. So our magnetic field is going from north to south like this. Our current is moving actually in two different directions. On this side it's moving in this direction, and on the other side it's moving in this direction. So what we are going to have is that when the wire is moving past the south bit of the magnet, the force is going to be going down, and when it's moving past the north face of the magnet, the force is going to be going up. And because one side is being pushed down, the other side is being pushed up, it is going to turn around.
Awesome work for making it to the end, guys. I know this video is a slug to get through. The rest of this is physics only.
A fluid can either be a liquid or a gas. Liquids are incompressible. And the examples like that word. Whereas gases are compressible. Pressure with a P equals height times density, which is a lowercase rho, times gravitational field strength. Pressure is measured in pascals, height is measured in meters, density is measured in kilograms per meters cubed, and gravitational field strength is 9.8 newtons per kilogram. The moment equals force times distance. Moment is measured in Newton meters. Force is measured in newtons. Distance is measured in meters. If our forces are unbalanced, for example, if this force is bigger than this force, we're going to have a turning effect, whether that be clockwise or anti-clockwise. If they are balanced, if this force and this force are the same, then we are not going to have a turning effect. When we have static electricity, we have an object that isn't normally being charged becoming charged. That happens when two insulators rub together. This is caused by the movement of electrons from one thing to another thing. And you're going to get a shock when the charges reset when you touch something metal. If you have two charged objects coming together, they're going to repel each other. Alternatively, if you have a charged object and an object which has the opposite charge, they're going to attract each other. A moving coil loudspeaker works by making a diaphragm attached to a coil vibrate. When we have a current passing through the coil, the force that is generated via the motor effect makes the coil move. Every time the current changes direction, the force reverses direction. So the coil is going to be going back and forwards, making the diaphragm go back and forward, generating sound waves. A moving coil microphone works with the same principle but in the opposite direction. Sound causes the diaphragm to vibrate. The diaphragm is attached to the coil. The vibration of the diaphragm moves the coil, which is going to cause the coil to move backwards and forwards past the magnet. In a transformer, we have a soft iron core. We have a wire which is going to be coiling around, and you notice there are a different number of coils here. We are going to be looking at varying the number of coils so that we can vary the voltage that goes into and comes out of our transformer. If we have a step-up transformer, the secondary voltage is going to be greater than the primary voltage, so the voltage coming out is going to be greater than the voltage going in. If we have a step-down transformer, the secondary voltage is going to be less than the primary voltage, so the voltage coming out is going to be less than the voltage going in. When we are looking at transformers calculations, we have voltage in the primary coil divided by voltage in the secondary coil equals the number of turns in the primary coil divided by the number of turns in the secondary coil. Our units for this are going to be for voltage, that is volts, and number of turns doesn't have a unit because it's just a number.